which is very bad, of course. I have no other word for it. There may be one student who couldn't come because he couldn't use his bicycle. Yes. Yes. So he is not here in the audience. But if you meet a student who couldn't come because he couldn't use his bicycle, please tell him or her that we left the keys at the secretaries. There's some text on the bicycle. It's a holy text, yes. Sao Lorenzo, yes. And then MG. So this is the information. Now we go over to the scientific part, and Philippe Courteille will give his third lecture. Please go ahead.
Scientific information.
Yes.
Agora melhor? Agora. Tá, okay. Yeah, good morning. So yesterday we stopped with the derivation of the Bloch equation in the interaction picture, which can be given in this nice matrix form. I will zoom a little bit to make it larger. Let's see if I can do like that. So this is these are the Bloch equations in the Schrödinger picture, and then we went on to transforming into the rotating frame, and the final form of the Bloch equations that are very common and very easy to use for computer simulations is this one. This is matrix form. And the equation is this one, okay? And these are the definitions of the matrix and of the Bloch vector. You will notice that there's not yet a spontaneous emission in there, and the next step will be to include spontaneous emission. We already learned how to do this for the Schrödinger equation, so for the probability amplitudes. At the very first lecture, I derived an equation for the coefficient dA. So the time derivative of this times the imaginary constant was given by the Rabi frequency times the oscillatory behavior of the Rabi frequency times this exponential functions, and this is related. So it's a two-coupled differential equation coupling A2 and A1, and there's a probability amplitude for the atom to be in the lower state 1 on the upper state 2. And then in the second lecture, I also derived using this simplified Wigner-Weisskopf theory, I derived another equation, which is actually this here. So this is so here you have the stimulated part. So if you have a laser frequency omega, then you can make Rabi oscillations between the two states. And this is the first equation. The second equation is if you have some population in the excited state, then you can have some spontaneous emission with a rate gamma, which is this rate. Okay. So and now it's easy. You just have to combine the two equations. Okay. So we just take these equations and I just add phenomenologically the second term here, and then you have combined both. No? You have combined stimulated emission and spontaneous emission. Okay. Now this you would do for the amplitudes, but you can use the same trick for the Bloch for the density matrix. Simply remembering that ρ22 is equal to A2 star A2. So it's the population of the excited state. Now if I derive d ρ22 in time. Okay, then you have here you have to derive the first coefficient and then the second coefficient. This will give you a factor of 2. Okay, so then I can go from let's say from this equation. Formally, I can go from this equation by making the following substitution. I substitute the original time derivative by a time derivative plus spontaneous decay. Okay, so if I take the original Bloch oscillation equations and I do the substitution of the time derivative like this, you get automatically inclusion of the here's missing the gamma. You get automatically the decaying term. And this trick you also apply here, but here you gain a factor of 2. Okay, so this. If I want to do this for rho, then I have to do the substitution of the time derivative plus gamma, so which is twice this factor. Okay. Now, if I want to know the time evolution of the coherences, okay. Now remember that the coherences is given by this expression, and here the state 1 does not decay, so this is not subject to decay gamma, but only this is the state A2. So here, upon derivation, you do not gain a factor of 2. Okay, so here I get the same rule, substitution rule as here. Okay. Now this is phenomenologically this to derive quickly the correct shape of the Bloch equations. It's of course possible to show this strictly by a complete Weisskopf-Wigner theory, which is much more elaborate. But this is not what I'm going to do here. Okay. Now I showed you last lecture how to solve. Formally the Bloch equation. I showed you already that a nice representation of the Bloch matrix is also using the Bloch sphere. So it's a sphere where the Bloch vector rotates on top of the sphere, which has always a length of 1. So it's really on a sphere. The motion of the Bloch vector. It can make precession. It can make nutation. Yeah, there's a question.
You said that there is the process of spontaneous decay is random, right?
Yeah.
But like, wouldn't this equation imply that there is a characteristic time, so like that some population, then the time scale gamma after the population decay?
Yes, this is exactly what happens. So here it would happen, but this is amplitude, no? But it also will happen if you have rho 2, which is a population, which is an observable. This is what you measure in the experiment. And yes, after some time, if you prepare your state in the upper level, and you don't irradiate laser light, the evolution of the Bloch equation will show you that the population decays exponentially.
So there is a time structure, like what gives this time structure?
Yes, and the decay rate is gamma. This gamma here.
But like it's, can you derive a theory for gamma in some way?
Yes, I will show you just in a few minutes the result of a calculation. The calculation itself is complicated, but I will show you the result. Okay, so and now what you do is also empirically the following. If you have an initial population of state 2, okay, then gamma is telling you an exponential decay. That means that you expect that the population of the excited state, which is actually rho 2, decays exponentially within a time. Here's 1 over e. So this time would be the decay rate 1 over gamma. Okay. So this is what you would expect without laser light, simply decaying from 1 to here's 0. Okay. Now, if you don't have a laser light, you don't even need to have all this off-diagonal elements. You don't even have you don't excite coherences. You don't excite really a dipole moment. All you have is a decay of population from the upper state to the lower state. Okay, and this means that you have a rate equation. Okay, so writing down, I can immediately write down the equation of rho to 2. So answering to your question to some extent, rho to 2 is just given by a decay, exponential decay. So I know that in the absence of a coupling of the two levels, this will be my solution. And actually, if rho to 2 initially is 1, so the population is in the upper state, this will just be this. Okay. Now this I can incorporate directly into the Bloch equations. And I do this like this. This is exactly the Bloch equation, the Bloch matrix that I had before. There's only a very small difference. There's a difference here, gamma, and minus gamma here. If you read the second equation, you set now in your mind omega equals 0. Then all the non-diagonal terms here disappear. You only have diagonal terms, okay? And except for this gamma here. And then what you get is an equation reading the diamond derivative of rho to 2 is equal to minus gamma times rho to 2. And this is exactly what I've written here. What I've written. Yes, this is already the solution. So I write it explicitly. Rho to 2 time derivative is equal to minus gamma rho to 2. And the solution of this equation is exactly this. So I just incorporated by hand the rate equation into the Bloch equation. Okay. By this minus gamma. But of course, if I lose population in the state 2, there must be another state gaining the population, and this will be state 1. And this is the gain term here. So you have the other equation, rho 2, 2, rho 1, 1. The time derivative is equal to gamma rho 1, 1. Rho 2, 2, no? Sorry. So rho 1, 1 is equal to gamma 2 times gamma times rho 2, 2. Okay. Of course, this is a conservation of probability because I know that rho 1, 1 plus rho 2, 2 must give 1. So this is so easy to understand how you can include spontaneous emission at this place. I said here that that the population decay with gamma, but I also said that the dipole moment decay with gamma half. So the dipole moments, the decay of the dipole moments is here and here. Okay. So we have also equations where rho 1, 2 is decaying with the rate gamma half. Okay. So, and this is now the exact Bloch equation for a two-level system. And you can extend this for arbitrary numbers of levels. You just have to define in which direction your spontaneous emission is going. No? So for example, you have a three-level system. We'll see this a little bit later, like this. So you will have spontaneous decay here, you will have spontaneous decay here, and you will have spontaneous decay here. But you will not have spontaneous decay from level 1 to 2, or from level 2 to 3. Okay? And just by thinking about in which direction the spontaneous emission is going, you can figure out the rate equation, and put your empirically or phenomenologically your decay rates in the right place. The rest here of the matrix is given by the Liouville equation. So there's no choice. This comes automatically out of the formalism. The rest here, the non-diagonal elements. But the spontaneous emission you put by hand. I will tell you a little bit later how you can also derive them from a theory without doing this empirical considerations. This is called probably many of you already know the term of Lindblad term. So it's a dissipative term that you get if you derive the master equation from the Liouville equation doing the Weisskopf-Wigner theory. But for the time being, let me now analyze a little bit this guy here. So now, since we have now a spontaneous emission, we have dissipation. That means that we expect that the system will come to equilibrium at some point, because there is no friction. Okay. So we expect that a driven to level system will not do Rabi oscillations forever, but that the Rabi oscillations, at some point they will decay. So initially, you may have some Rabi oscillation, but eventually they will decay and they will come to an equilibrium. And this equilibrium here cannot be larger than 1/2, because if it was larger than 1/2, you would have inversion, which corresponds to negative temperature, which is not possible. Okay. So this asymptote, the maximum you can get is 1/2. So you cannot have some stationary solution here, because this would correspond to a population which is higher here than here. But the distribution of the population on the energy level has to satisfy the Boltzmann law. So you have energy over K Boltzmann T. And this is a curve which looks plotting this here with. So this is a probability to find your system at some energy. I plot it now in this direction. Then the exponential decay. So this exponential will look like this. And this is a probability with amplitude, which means that the probability for the system to be in lower state is always higher than to be in higher state. You can only invert this here by having here negative temperature. So temperature below 0 Kelvin. Okay, this corresponds to non-equilibrium state. So in equilibrium, in thermal equilibrium, when the Boltzmann law here is valid, you cannot have a population of more than 1/2 for this simple reason. And if you solve the Bloch equation, you will find that this satisfies this. It's actually not possible to drive, in the presence of spontaneous emission, to drive two-level system in such a way that you get inversion in the long time regime. You can have it for short times here. You can make a pi pulse. But if you have a spontaneous emission, eventually you will have decay and it will come back to.
But that's without laser.
No, it's with laser. So it's with laser. So you have a laser here. You have absorption, stimulated emission, and stimulated and spontaneous emission. Without laser, either you start in the ground state and then you have nothing, or you start in the excited state and then you have exponential decay, which also goes to 0 and is also below 1/2. But with exponential decay, with gamma, even if you have a laser light, you will never be able in the infinite time limit to have an inversion. Okay, and then this you can also find by directly solving this. And actually, the stationary solution, that means the solution where there is no time evolution anymore, is easy to derive from this. No? So we say, okay, if you take infinite time, if you take time to infinity, then the derivative of your population does not change anymore. Okay, it's damped out here. It's constant, and the derivative of constant is 0. So if you say that for infinite time, all my populations and all my coherences are 0, with this condition, you can solve this equation easily, and the result, you can do it as an exercise, the result is this equation here. And so this is a stationary population of your two-level system at infinite time, and this is your coherence. So you see, let's for simplicity go on resonance. So delta is equal 0. So your laser fits directly the energy difference. Okay, and now you see that let's assume that your Rabi frequency is very strong. You have a very strong laser, so strong that you can even neglect spontaneous emission. Okay, then you see that this gives exactly one half. So the best you can do if you have a very strong laser is make this stationary population one half. But if you have spontaneous emission, then it will always be smaller than one half. You have the same denominator on this side here. Okay. But it has a different dependence on detuning. For example, here you have, if the detuning is very large, then you have a term like omega squared over the detuning squared. So it goes like 1 over the detuning squared. Here it goes like 1 over detuning only, linearly. Because if gamma is negligible, you have delta over delta squared, which is 1 over delta. So we'll see later that this term here is responsible for radiation pressure forces, and this term here is responsible for dipolar forces. So dipolar forces are very strong, even very far from resonance, but the radiation pressure is always very small if you are very far from resonance. And this is very good because you can use this feature for making conservative potentials which are not subject to radiation pressure force. But we will see this a little bit later. Now here, this looks like a Lorentzian, but the width now is not the national line width. So this is interesting that normally you would say, due to the fact that I have decay here, the width, this corresponds to width of my excited states of gamma. So if I could make an experiment trying to resolve the width of this state here, I would find the spontaneous line width gamma. But if your laser is very strong, so strong that it's larger than that omega is larger than gamma, then you have an additional line broadening mechanism, which is called saturation broadening or power broadening. And this power broadening not only affects the upper state, so the real width here then is omega rather than take another color. So if omega is very strong in comparison to gamma, then it's dominating the line width, but this also applies for the ground state. Okay? So the gamma is only affecting the width of the excited state, but the power broadening affects both the ground state and the excited state. So if you later on want to do a spectroscopy of the width of your ground state, for example, with another laser scanned through the resonance, you will not find the infinitely small line width of a ground state, because normally a ground state is stable, has no line width, but you will find actually the width imposed by the laser beam driving this transition. Okay? So the power broadening affects both the line width of both levels. Where did I put this? And this is the line width here, no? Okay, so if omega is strong, then it will dominate the effective line width, which is given by the denominator here. Then you can also give it a different shape. That's very common in this field of physics to define a saturation parameter. And it's defined in this way. So on resonance, it would be just the relationship between omega squared and gamma squared. So saturation, if you saturate a transition, that means this is a point where your coherence is dominating dissipative dynamics. So it's your Rabi oscillations are faster than the spontaneous decay. And this is, if you do quantum information, for example, this is what you want. You don't want spontaneous emission because this is killing your information. What you want is coherent oscillations, coherent dynamics. And then you need to choose a transition where gamma is sufficiently small, so that your dynamics is dominated only by omega. So it's reversible, you can do all kinds of operations, unitary operations. And the saturation parameter is exactly a parameter which measures this. So with this definition, you can simplify a little bit this formula, and they look then like this here. It's actually a very simple form. The square of the dipole moment, the stationary dipole moment, has also a very simple form, looks like this. So here I made a small simulation. You can download the simulation by clicking on here and run it yourself. What you see here is this is time axis, and here you ramp from here to here. You ramp up the Rabi frequency. So it's not so easy to see here, but yes. So the initial condition is initially the state, the atom is in the ground state. So nothing is happening here. It's staying zero if there is no laser light. But here you excite the first Rabi oscillations, which then quickly damp out. And the frequency of the Rabi oscillations, they are exactly the Rabi frequency. So if you crank up the Rabi frequency here, you will have faster and faster oscillations, which at some point, which at some time, which corresponds always to the decay rate gamma, will fade out. Or you can also choose to visualize it in the Bloch sphere diagram. Here I calculated the Bloch sphere for two situations. So first I applied a pi pulse. So I let the atom evolve from the ground state to the excited state. And then I switch off the laser light. And what happens? The population goes straight down. Interestingly, the length of the Bloch vector is not unitary anymore. So the Bloch vector in the presence of spontaneous emission can be lower than 1. And this shows that you evolve into a mixed state during this spontaneous emission. So it's not a pure state anymore. The green curve here, what I did, I did a pi pulse, but with a small detuning. Okay. So if I have a detuning, I will excite in the same time a dipole moment. So the atom is trying to rotate in the equatorial plane. Additionally to this notation, to this movement of population up. And then I switch off the laser light here, and then it spirals down, but to the same final point, 0 of course. But you have now a different dynamics. So if you don't go to a pure population of the excited state and then switch off the laser light, but if you excite a coherence, then you have additionally this rotation, this precession. And all these, all you need to do these kind of calculations is the matrix that I show you. So the trick here the problem is the following. You have a time-dependent Hamiltonian. The time-dependent Hamiltonian comes from the fact that you first need to switch on the laser light to put the atom up, and then you switch off the laser light to let it evolve under the rule of spontaneous emission. So if I go back to my matrix here, so this is what you put into your computer. So I have first to evolve to solve this equation from time 0 to some time which corresponds to the excited state population, including omega. So I put a laser beam. I choose the laser beam, for example, on resonance. So I let delta here be 0. But I choose it in such a way that I get population, all my population up. But then I switch off the laser and let it undergo spontaneous emission. And then I take the new initial conditions, which is all my population is in the rho 2, so rho 2 equal to 1. And I solve again the Bloch equations with these new initial conditions. So what you do basically is you have your solution. This is your equation, okay? This is your Bloch equation, let's say, and this is your Liouville matrix. Then you say, okay, now the Liouville matrix depends on time. So you have an equation like this. So if actually your manipulation of the physics of your system can be even more complicated. You can make a ramp. You can slowly switch on a laser light. You can do all kind of stuff. Then what you do is the following: you calculate your vector rho at some time t plus dt. Okay, and here you write the formal solution would be e to the a times dt rho t. Okay, and then you start here with an initial condition. You solve this matrix, so MATLAB does it for you. Okay, and then you get a new Bloch vector, and then you take this as a new initial condition, and you put it here. Okay, with a new Liouville operator, where maybe you switch off the laser light, or you change the detuning or something, and you do this iteratively as long as necessary. The only condition is that the time step dt must be small in comparison to the variation that you apply here. Okay, so if you have your detuning, for example, you choose to make a ramp in time, your laser with an acoustic modulator or so, you make a time-dependent detuning. Let's say this is 0, like here. Then that means that your Liouville operator is changing gradually, and then you must choose your time step dt in such a way that during this time your matrix does not change too much. Otherwise, you make discretization errors. Okay. But this is actually the way that these simulations have been obtained that I've shown. So it's actually quite easy to do this simulation, and you can make much more funny stuff with this. Okay, there are more broadening mechanisms. So I already talked about saturation broadening. There's also collision broadening. So if you have not only one atom, but many atoms, so they can undergo collisions. So Jörg Walraven is talking about this very profoundly. We will not go into the details here because this is not interesting in this context. But imagine that you have two-level atoms, okay, and then they are now approaching. What happens? You will have van der Waals forces, and these van der Waals forces, or any other force, will distort your orbitals, the electronic orbitals. That means that your energy levels here, they will be deformed. For example, like this. Upon the collision. So if the atoms approach each other, they will see their orbital energy shifted a little bit. Now imagine that you shine in a laser beam in your sample. The laser beam is made to couple two states which are of atoms which are not interacting. Now why this atom that is excited here and is making Rabi oscillations here, while this atom is approaching another atom, it will come out of resonance because at this point, it's not in resonance with the laser anymore. And this means that the evolution of the Rabi oscillation is strongly perturbed. And it comes down to a disruption of the coherent evolution of the Rabi oscillation. But what does not happen, or mostly does not happen, is that population changed. So if your population is here, then it will change. It will go up here and it will come back here, but it will not make a transition. Yeah? So generally, it does not make a transition. So the only thing that really happens in a collision is that the dipole moment is perturbed, but not the population. Or in other words, if I look at the maybe I should show it at the Bloch matrix. So what are the components here which change which are responsible for the decay of the population? Is this one, and this is responsible for decay of the coherences. So the only thing that changes upon the collision is that this gamma half you must substitute this gamma half plus the gamma half minus some term which comes from the collision. Okay, so if you have a strong collision rate, then this gamma prime will be strong. If it's negligible, it will be much smaller than the decoherence due to national decay. Okay, but this is luckily, this is the only correction that you have to apply, and so you have to add here a gamma prime in this diagonal element, and it will broaden your transition, but it will not change drastically the dynamics if the gamma collision is not too strong. So this is called, and since you can make this on average for all the atoms, we call this a homogeneous broadening. You can incorporate this broadening into the Bloch equation and get the correct result. But there are other broadening mechanisms where this doesn't work. And one example is Doppler broadening. So imagine that, I have to make a little bit of space. Maybe. So imagine that you have one atom here. So your laser is coming from here, okay? Making a Rabi frequency omega. You have one atom here moving in this direction. You have another atom here moving in this direction. Okay. If this atom is all the atoms are now two-level systems. Okay. If the atom is moving away from the laser, this will cause what? Doppler shift to the red or to the blue? To the red. Okay, that means that that if the atom was, let me draw here an atom which is not moving, so it's velocity 0, then this laser here, on resonance, it will couple the two states on resonance. But if the atom is moving away, then the two levels. So you have, let's say, you can plot it like this. The two levels get away, yeah? And so that you can, due to the Doppler shift, you can picture it like this: that the levels are shifted away, so that your laser gets to the red. Or you can also picture it in the other way around. You say, okay, my atom is the levels are in the inertial frame of the atom is constant, but it sees the laser redshifted. Okay, and it's the other way around. If the atom is moving towards the source. This is very important because this is at the heart of very powerful cooling techniques. Okay, but here the problem is for the description that for every atom you have a different delta. Okay, so the delta actually it depends on the velocity of the atoms. Okay, so it's you can write it like this. So the delta due to the velocity of the atoms is k, so the wave vector times the velocity. Or let's write it like this. So if you have an original delta without velocity, this delta will be increased by the velocity of the atom. So in fact, what you have to do is you have to solve a Bloch equation for every atom which has a different velocity. And since the atoms are belonging to different classes, to different velocity classes, this is an inhomogeneous broadening. So the broadening doesn't, it depends on the parts, on the class of velocity where the atom is located. So you have, and this distribution is actually a Maxwell-Boltzmann distribution if your gas is in thermal equilibrium. So what you typically have is you have a probability distribution in a thermal gas, which is given like this. So this is a probability density, and this is a probability to find an atom inside the velocity interval given by between v and z. V and V plus dVz. Okay, and this is typically Maxwell-Boltzmann distribution. dVz. So in fact, what you have to do is you solve for every velocity, you solve your Bloch equation, and then finally you make a convolution of your solution. So you have I can show it here on the script. Here. So instead of having so you solve the Bloch equation, the time evolution of the Bloch equation, or the stationary solution of the Bloch equation for every different velocity, and then you take the integral weighted by the probability of finding your atom in this velocity class. So this is more tedious, and what that means is that every spectroscopy, every line that you may resolve for a single atom will be broadened inhomogeneously by a Gaussian. Okay, so the collision broadening is a Lorentzian broadening, no? Because it's just the stationary solution of the Bloch equation was a Lorentzian with a Lorentzian denominator, and here you have a Gaussian. So you can always easily distinguish inhomogeneous broadening and homogeneous broadening. Okay. But there are techniques to avoid Doppler broadening. So for example, saturation spectroscopy. There are smart techniques. You have two counterpropagating laser beams. And these two counterpropagating laser beams, they interact with the same atom only if these atoms have zero velocity. Because if an atom is moving in this direction, it will see one laser beam redshifted and the other blue shifted. Okay, so it will not be able to interact with one of those two lasers. Then you can change the frequency of your laser beam, but you will if the frequency of both laser beams are the same, you will always have different velocity classes talking to your atom. Only those atoms which have no velocity in this direction are talking to both atoms, and you can use this trick in order to make spectroscopy only limited by the national line width of the atomic transition. But this is not possible for homogeneous broadening, okay? Because homogeneous broadening, all atoms are affected by this broadening, and not only some classes. There are other inhomogeneous broadening mechanisms, like if you have fluctuating magnetic fields. This is typical. So then you have your atoms are trapped, for example, in a magnetic trap. Then you have some part of the atoms which are maybe closer to some noise source, and which have see more magnetic field, oscillating magnetic fields. So for example, if you have atoms in the quadrupole trap, then the atoms which are in the regions where the magnetic field is stronger, those will be more subject to noise or so. And then it depends not on the velocity classes, but on the position classes of your atoms. No? But it's also an inhomogeneous broadening mechanism. Okay, now I promised that I give a little outlook on the way you can formally include spontaneous emission. And this is also a motivation to go to multi-level systems. So here I've put the Bloch equations in the following shape. So here you have the coherent part of the Bloch oscillation. Yeah? So this I call the coherent Liouville operator here, and you have an additional Liouville operator which I put ad hoc in the Bloch equation, introducing this gammas. Okay. But you can do this also in a more scientific way, like this here. So this is called the Lindblad term here. And it's basically easy to calculate once you realize that this is a Bloch, the Pauli matrices. Okay, and this is the density operator. And then you can easily check that for a two-level system, this is just giving exactly the gammas where I put them ad hoc. So we have here decay of population, and here this will correspond to the decay of the coherences. And this now you can derive from Weisskopf-Wigner theory directly. So the advantage is that you don't have to think where you have to put the gamma. It's however difficult to derive this term here. But the advantage of this term is that you can easily generalize it to a multi-level system. So here I put the master equation for a multi-level system. So you have here the atomic part, the electronic excitation. So these are the steady state, the stationary Hamiltonians. This is the interaction part in the semi-classical picture. So the photon is not quantized. And here now you have the Lindblad operator, which looks a little bit more complicated. But here you have the different decay rates between the different states that you may have. So E and J simply label the atomic states. And then you can just calculate it out. So forget about this second term here, the betas. The betas are additional broadening mechanism, for example, due to laser fluctuations or collisions or so. So you don't need to take this into account for the normal Bloch equations. For normal Bloch equation, just take this part here. And this is pretty easy to calculate. These are the generalized Bloch matrices. I defined them, not on this slide, but it's simply the following. So this guy here is nothing else than this here. And then once you have your multi-level system, you have to label all the states you are interested in, letting I go from 1 to, I don't know, 16, or how many levels you want to study. And then you can set up the Bloch equations. So just to give an example, I did this here for a three-level system, because in fact, if you understand the three-level system, I think you understand everything about driving the atomic structure. The two-level system is not sufficient because there are additional effects in three-level system, but you can how to say, break down any multi-level system in several three-level systems. So here are three different possibilities to realize three-level systems. So you have what you need to have is you say what transitions you want to drive with lasers. You cannot include in the Bloch equation the possibility to drive all three transitions, this one, and this one, because it would be an over-definition of your system. It would be like a three-body collisions, or the three-body problem. You cannot solve it. Okay, it's over-defined. But because you have to do transform into the rotating frame here, for example, and here. But if you if you do this for this transition and this transition, this is already defined, and you cannot do it separately for another laser on this transition. Okay, so but this is possible. So this is called a lambda system because it looks like a lambda. So you have spontaneous decay everywhere, but you only drive this transition and this transition. This is a V system. Okay. You can drive this guy, and this is a cascade system. And all these three possibilities to realize three-level system, you can cast into a Bloch matrix. This is a Bloch matrix, which is easy to read because you already know how to read it for a two-level system. No? So you just take, for example, you cut out row 1, 1, row 2, 2. So you cut out maybe the first two-level system here. You just consider these two rows, okay, and additionally these two coherences. If you cut this out, you just get your two-level system back. But you do this for all possibilities. So you have transitions 1, 2, 2, 3, and 1, 3. But notice that 1, 3 in this case here is not driven by laser light. So there's no omega 1, 3 here. There's only omega 2, 3 and omega 1, 2 because these are the two transitions which are driven. So it's these parts here. So this part of the matrix and this part of the matrix are very easy to set up. It's just to level. Which is a little bit more complicated is, and the only thing that is a little bit more involved is these parts here and these parts. And this actually means that you can also do transitions from 1 to 3 directly by a two-photon transition, or called also Raman transition, because you go from this state to this state directly. And this corresponds, and this couples, for example, state 1 with state 3 are coupled, or let's say state 3, so this one here, you can excite a coherence 1, 3 with laser omega 1, 2 and omega 2, 3. So this coherence is excited by the two other lasers. So you have to think a little bit where these elements are, in which order and which sign. But this is the only thing that is a little bit more evolved. And if you know it for a 3-level system, you can set it up for a 16-level system or for a 200-level system. That's easy. Actually, if you really want to set up this for multi-level system, you can follow a recipe that is where I give the link for alkali atoms or so. Just putting in the level structure is a little bit like a Q-tip. You give in the level structure, and automatically it set up for you the Bloch equations. But here there are many phenomena that you can simulate with this, which are impossible to see in the 2-level system. Like, for example, what are the phenomena? Oh yeah, and then here I said there are 3 different configurations, so lambda, V, and cascade. The only thing that changes if you define the levels like I did here, I label the systems like here. The only thing that changes is this part here, the rate equations. Because here you have a decay from 2 to 3, and here from 3 to 2 here, and from 1 to 2, no? And here you have from 2 to 1 and from 3 to 1. So in order to have the same matrix, so this matrix here is correct for all 3 possibilities, but you have to think about where the spontaneous emission is going. So I decouple this matrix a little bit lower here. So I think this is for the V configuration. It looks like this. I think this original matrix was for lambda configuration. This would be a V configuration, and it would be a little bit different for a cascade configuration. But this is the only thing that really changes. This is for the cascade configuration. Okay. Yeah. So you can what can you see in this 3-level Bloch equations? You can check Adler-Towne splitting. So not only the fact that the 2 levels are split by Adler-Towne, but also how to resolve it spectroscopically. You can study this, light shifts, dark resonances, electromagnetically induced transparency, Fano resonances, quantum jumps, needs a 3-level system, stir up, so adiabatic rapid passages, and all this kind of stuff you can easily simulate by simulating numerically your Bloch equations. There are many examples in the exercises. So you will see there are several nice curves. And if you're interested, it's like here. If you're interested in one of the exercises and you don't know how to do it, you can ask me. I can give you a hint. Here you see a splitting, Adler-Towne splitting of your 2-level system. This light shift, and so on. So I will not stop here, and I have to now to go to the next topic. So since we want to talk about atom optics, at some point we have now to talk about the external degrees of freedom. Huh? I already took a look a long time before we got there. But finally, we have to start to talk about this. Okay, the first thing is I want to talk about magnetic trapping. So interaction, how do atoms interact with magnetic fields? So for this, I have to introduce first the alkali atoms. Alkali atoms are atoms which are very close to hydrogen. So they have a very simple, relatively simple level structure because there's only one valence electron out there. So we can basically solve, at least for the structure of the outer electron, the same what you learn for hydrogen atom. Okay? Also, the lowest transition for alkalis are in the visible. That means you can experimentally address these transitions, and play around and use them for cooling and other things. So it's important that you have laser tools or technological tools in order to play with your atoms. So for alkali atoms, luckily this is the case. There's another reason. It is relatively easy to make vapor pressures. So you can just by heating a little bit the sodium, you can get a reasonable amount of atoms in a gas phase and do spectroscopy. It's a little bit more complicated for strontium, where you have to heat to higher temperatures. No? But it's also not an alkali. So alkalis are very nice for doing this kind of studies, and these almost all alkalis have been condensed nowadays. No? And so these are the elements which are easiest to manipulate in the lab. Now the level structure is very easy because you have one electron in the outer out of closed shells. That means that this electron have a angular orbital momentum, L, but it also have a spin. So you have two quantum numbers, Ls, but you don't need to consider the coupling of this electron spin or orbital quantum number with other electrons because there are no other electrons. Okay. Now what you have is, if you have a spin, the spin can create a magnetic dipole moment. The motion of the electron around the nucleus corresponds to a current, which makes a magnetic field. So you have an interaction between the spin with the magnetic field created by the motion of the electron. This is called LS coupling. So it's LS coupling. And this gives rise to an energy which is given by this. So you have it's proportional to this LS, where LS here are now quantum numbers or operators. Okay. Now, so you have to understand how these operators couple. Now, so in simplified pictorial representations, I like to draw it like this. If you have two vectors that may couple, if the coupling is strong enough, no, then you will have a good new quantum number, which will be the total angular momentum resulting from this coupling. And this is typically coupled J. But you have a level structure which is due to this coupling, no? And this is called the fine structure. This is exactly what you learned for the hydrogen atom, and this is the fine structure for the sodium atom. So on the left side here, no? So we have one transition from here, this notation, I think you will probably remember. So no, it's like this. I think this is called the Russell-Saunders notation. The L is here, the J is here, and here you have 2s plus 1. Okay, so the spin, since you have only one electron, the spin is necessary 1/2. Okay, 1/2 times 2 is 1. 1 plus 1 is 2, so we have here a 2. So the ground state is a 2s 1/2. So the 3 is the main quantum number of the electron. But typically you write here small 2 on top of the S. So it's 2s 1 half. And 1 half, S means that L is equal 0. Okay. P means that L is equal 1. And this is J. J is equal to 1 half and here is either 1 half or 3 halves. This is a fine structure. Because the J here must be, can have all the quantum numbers between L plus S and L minus S. So L minus S, J, L plus S. So since in this state here S, L is 1, okay, so 1 plus S would be 3 half, L minus 1 half would be 1 half, so your J must be between 1 half and 3 halves. So these are the 2 states. So now they are very different. They're very far away from each other. So 0.6 nanometers. No? For laser standards, this is infinitely far away. However, all the alkalis and many other atoms have also a nuclear spin. Okay, so the nucleus here can also have a spin, which is called E. Now the nuclear spin can also couple to the total spin of the electron. So we have here I. Okay. And now J couples with I, and to a new quantum number, which is called F. And this is a hyperfine structure. So for sodium, for example, if I remember correctly, E is equal to 3 half. But it depends on the isotope. No? So rubidium has several different isotopes, and for the isotopes, they are different by the fact that they have different nuclear spin. Okay. And this is also very important for another reason, because the total the total quantum number F, no, which is again can take values between I minus J and I plus J. Okay, so you have here a hyperfine structure of the ground state. So the splitting is 1.7 gigahertz here. Oh, this is a mistake. So this is I have to correct this value here. It's not. It's smaller. So you have a hyperfine structure which dominates your atom and everything that you can do with the atom. Now, another reason why this is important: if the F is integer, then you have a boson. If it's semi-integer, then you have a fermion. And this determines whether you can make a Bose-Einstein condensate or not with your atomic species. Okay. And this depends on the nuclear spin J, on the coupling of the nuclear spin J, and the nuclear spin I, and the total spin of your electron J. And if F, the coupling, is either integer or semi-integer. No? If it's semi-integer, it's a fermion, and you cannot Bose-Einstein condense. They do not collide. Okay. Now, why do I have to do a little bit atomic physics? Because now, so you can calculate the hyperfine structure. So the important formula now is here. You have the Zeeman effect. So the dipole moment, μ, of your atom interacts with external magnetic fields. And the dipole moment is given by the total spin. So this here, this μ, this is what you learn, the Zeeman effect that you learn in atomic physics. You can write this as G. So this is a Landé factor. If you have a hyperfine structure, in the general case, you have a GF times the Bohr magneton times the magnetic quantum number F, MF, times the magnetic field. So if you typically you take quantization axis in Z direction, this is your interaction between the atom, which can be in different states, and your magnetic field. So I calculated here the energy of the Zeeman shift for, I think it's also sodium, yes. Again, you can download the program to calculate this here. And depending on the hyperfine state where you are and the Zeeman state where you are, you see in the magnetic field different behaviors. So it goes down, it goes up. Okay. And this depends simply. So here you are in the Zeeman regime, where this formula is good. So here MF for a transition where f equal 1, MF can be -1, 0, or +1. So you have this would be the case, for example, for this level here, f equal 1, you have 3 states here. If f equal 2, then you have 5 Zeeman states, which split up. Now, when you go to strong magnetic fields, then the linear behavior, here you have a linear behavior because if you crank up linearly the magnetic field, the energy will be linear also because m is a number, and the numbers are all different by one unit. However, you go into another regime where the splitting breaks up, so the splitting between I and J breaks up, and then the whole picture between the I-J coupling is not good anymore, and this is called the Paschen-Bach regime of the hyperfine structure. It's also called the Paschen-Goodsmith regime, where you change the coupling of the coupling scheme of your spins, and then it's not the total quantum number which couples to the magnetic field, but the projection of the individual quantum numbers. They interact individually with the magnetic field. Okay, and so the two extremes are easy to understand here and here. But the transition, the dynamics of the decoupling is a little bit complicated. So this is why it's rather complicated here. But let us, for our purpose, only stick to the Zeeman regime, which is at very low magnetic field. What is now interesting, so you can calculate the G factors. Here, that's important if you really want to do calculations. The GF factor here, you can derive from atomic physics considerations. It's this term here. This is the coupling to the nuclear spin. And here you have the Landé factor for the electron spin, which is then given by this formula, which is, so here you have the fine structure, here you have the hyperfine structure. And using this formula, once you know in what state your atom is, then you can determine the final GF, which determines your magnetic field. So this is how you do it. But the useful physics for us will come later. So I will skip this part here and go directly to magnetic traps. So this formula we already had. And so notice, yeah, I remind you that. So let's consider a simple example of 3 levels, F equal 1, this is energy, and this is magnetic field. Okay. Now assume that you make in your lab a magnetic field, for example, using 2 coils in anti-Helmholtz configuration. So you have a current running through this coil in this direction, and in the contrary direction in the other coil. This magnetic field configurations makes you quadrupolar potential, which consists in a linear dependence of your magnetic field on the distance from the center here. So in the center you have 0 magnetic field, and if you go away a little bit away from the center point, you will have a linear increase of your magnetic field strength, of the absolute value of the magnetic field strength. So what you do is simply you go back to your electrodynamics course, and you calculate using the Biot-Savart law. Then you calculate the magnetic field dependence on space, and then since we are only interested in the region very close to the center, you make a Taylor expansion for small deviations from the origin, and you will see that this Taylor expansion is linear in Z and in R. Okay. So here I give the formula for the magnetic trap. See, here's a nicer visualization of the quadrupolar potential. So you have here anti-Helmholtz coils. This is the field lines, okay? And in the center, the field lines, they will compensate, and you get linear dependency. However, there is also a maximum here. So if you go very far away from your coil, then the magnetic field goes down again. Okay, so you have here 0, linear, but then it drops also if you go away from the coils. That means that your potential is not infinitely deep. So this depth here, this is the depth from the potential, is a distance from here to here. So if you trap atom in this potential, the atoms must be colder, they must have less kinetic energy than the height of the wall. So let me go back a little bit here to this formula. So we are now talking about forces for the first time, and trapping and all this kind of stuff. And how do you calculate this? Well, you calculate this using this interaction Hamiltonian with the different coupling degrees of freedom. Here. So it's this formula actually, yeah? So you can use this. So the force is always the gradient of an energy here, of a potential. So this is the way you calculate your force. Only if there is no external degree of freedom in your Hamiltonian, you cannot calculate anything from this formula. So you need to put in your interaction Hamiltonian something which depends on position. Okay. So what you do is actually you use the Hamiltonian that I've put onto the wall at the very first, at the beginning of the lectures. So you have the coupling between, is it visible here? No. So e to the EKR. Then you have the photon creation operator, and you have the de-excitation operator. Okay. So this is the interaction Hamiltonian is here. Okay. And so this is the coupling, and the coupling goes with the Rabi frequency that I've already defined. But the Rabi frequency can also depend on space. So for example, a laser beam here, when your atom is here, you will have a strong Rabi frequency here, but if your atom is here, your Rabi frequency will be 0 because it's simply not in the laser beam. Okay, so you have a spatially dependent Rabi frequency. And this is the position is to be considered as an operator. And so actually, if you want to calculate the force, you have to calculate take the interaction energy, but you have to put these terms, which are essentially the photonic recoil and the position-dependent Rabi frequency, you have to consider. You have to put them into your interaction. You cannot neglect the position dependence of your Rabi frequency, and you cannot neglect photonic recoil. They must be there. Okay. And now, yes, now you have. It's just a matter of doing theory, working out this gradient. Now, in this case here, now if in the case of our quadrupole trap, the magnetic field is space dependent, so we can actually calculate the gradient of your magnetic field, and this gradient is what is finally trapping your atoms. But remember here, the MJ can be positive or negative. So the force can be positive or negative. So the atoms can be expelled from your magnetic field or can be attracted towards the magnetic field. It depends on their internal state. And this is why the internal state of the atoms is so important. You cannot just treat the atom as having no internal structure. It's the presence of the internal structure which allows us to exert forces on the atom. So for example here, remember you cannot make magnetic field maxima in free space. This is forbidden by Maxwell's equation. You can only make magnetic field minima, for example, like in a quadrupole trap. It's a very popular trap. So in this case here, and this means that you can only trap low field-seeking atoms. That means atoms which want to lower their energy by going to the field minimum. You could also think in trapping high field seekers, but you see that it's negative here, and they will be expelled from the trap. You would have to construct a magnetic field configuration where there's a field maximum here to invert this here and to get a dependence where the atoms are trapped towards the maximum. But this doesn't exist. Okay. So and this is a little bit a nuisance because what you are trapping is never the lowest state in your system. It's not this state that you are trapping. This is the real ground state, but you trap always a state which is not the ground state, and this state is eventually subject to decay mechanism, and this can lead to unwanted effects. But normally this is not such a problem because the spontaneous decay rate from here to here is almost zero because these frequency differences are very small. They are in the order of megahertz and not of in optical frequencies like terahertz or so. Okay, so this is your potential, and now comes into play a problem which is called the Majorana spin flip problem. And the thing is the following: as long as I try to illustrate it here, as long as the atom is slowly moving in your magnetic trap, it can always adiabatically align its quantization axis to the environment. So it's an adiabatic movement, but at any time your atom is aligned to the magnetic field. This is only possible if the atom is moving slowly. Now, if the atom is coming close to the center here, then there is an abrupt change because the atom wants to go down here and to go up again here. But this is infinitely steep here. If you take the derivative of this here, it's a step. Okay, and this means that when the atoms are down here, there is a time where they see an abrupt change of the potential, and abrupt changes of the potential in perturbation theory we learned that they always cause transitions. And the transition in this case is simply that the atoms go from the trapped state to the untrapped state. So they make a transition from this state to this state, and they are expelled from the trap. Okay, so this is called Landau-Zener transition. And if you do the calculations, I put the calculations in the script. You find out. So this is a magnetic field for the magnetic potential. You can calculate the density distribution and everything. So what you have to compare in order to make sure that your movement, that the atomic movement is adiabatic, is you have to calculate the Larmor frequency, which is the frequency corresponding to the interaction of the atom with the magnetic field, with sudden changes of the magnetic field, which you can express like this. So as long as the Larmor frequency is larger than this, everything is okay. But if this is not valid anymore, then you can undergo transitions. And from this consideration, you can, for the quadrupolar trap, derive time constant for the spin flip. You can look at this in detail in the script, which is proportional to 1 over the temperature squared. That means that the more you cool atoms, you want to make a Bose-Einstein constant. This is finally always the goal. No? The more you cool the atoms down, the more you have a problem. Because the more you concentrate the atoms in the dangerous region where there is a hole, your magnetic field has a hole. Yeah? And the more you concentrate the atoms at the bottom of the potential, the more you have the probability of losing your atoms. Of losing your atoms by these Majorana spin flips. Here. So the colder your atomic cloud, the more it will be concentrated in the low part here of the magnetic trap, and will be subject to these losses. So this is why it took very long time for atoms to be Bose-Einstein condensed, because this is really the easiest trap that you can make in the lab. Actually, for hydrogen, it was a very big problem, and it made it it's easier to resolve this problem for other species rather than for hydrogen, and this is why hydrogen was condensed much later. This is why Dan Kleppner couldn't get the Nobel Prize for that, but other people. Yes, so, but there are possibilities to avoid this. There are 3 different possibilities which have been realized in the lab. The first one is a so-called top trap, which is illustrated here. So you have a quadrupolar trap here, but additionally you have a homogeneous magnetic field made by 2 opposed coils. Yeah? But in fact you have 4 opposed coils which are driven by a magnetic field, an oscillatory magnetic field. So what if you do it right? What happens is that 2 pairs of coils produce a homogeneous magnetic field at one instant, and the next instant you have the other 2 pairs which produce a magnetic coil, and then these again, but with a different polarity, and so on. And this means that you have here a magnetic field which rotates in space, a homogeneous magnetic field, which is superposed to the quadrupolar trap. So what it does, it displaces the hole at some distance. And if you do it quickly, then the atoms they do not notice this rapid oscillation of this hole. So you see a potential here, which is oscillating very quickly, but the atoms stay in the center. And if you do it right, then the hole will always be surrounding the atomic cloud, but it will never be in the place where the atoms could undergo this Majorana spin flip transition. So Eric Cornell was the first guy who used this technique. It's easy to implement. We also did this in the University of Texas, and we were able to make Bose-Einstein condensation with this trick. Then there's another possibility. Wolfgang Ketterle realized an optical plug. Or let me first talk about the Joffe-Pritchard configuration, or called magnetic bottle. So you can have strong currents in 3 Joffe bars here, plus a magnetic bottle field here, which is it's making a homogeneous magnetic field, but not really homogeneous. So it's a Helmholtz configuration, but since the distance is longer than the radius, so you have a deformation of the magnetic field along this line. And if you calculate the magnetic field for this configuration, you will have a potential looking a little bit like this. So even if you are in the center of the trap, R and Z is equal to 0, you still have an offset. So you don't have a position where the different Zeeman levels actually touch each other. So you cannot make a Majorana spin flip in this configuration. So this is used by many groups nowadays. Even in San Carlos, they use this type of idea. This is the idea of an optical plug. So you can, this is a condensate. If you take a focused laser beam, you can burn a hole in your condensate. So if the light is detuned to the blue of an atomic transition, the atoms will be repelled from the position where the laser beam is. Okay, and that means if your plug now is, if your quadrupole trap has its hole exactly here, but by putting the laser beam on top of this hole, you get the atoms away from this hole, and they cannot be subject to Majorana spin flips. You just push the atoms away from the dangerous region. This is also used in San Carlos, no? But it's difficult to align this because this laser beam has to be very small, and the Bose-Einstein constant is very small. You have to find the right position. It's not so easy to implement technologically. Here you see the density distribution along the Bose-Einstein constant. You really see that your density is reduced at the position where the laser beam is crossing this. So I will talk a little bit later now about how to exert forces with laser beams on atoms. I will do this actually in the next lecture. This lecture I will just like to finish with another trick, which is called Adiabatic Potential. And this works to understand this, we just have to remember the notions that we already acquired when discussing the light shift. And works like this. Imagine you have a magnetic field. Do I have somewhere? Yes, you have a picture. Now a quadrupolar magnetic field. So you have, let's say you have F equal 1/2. Your hyperfine structure state is F equal 1/2. Then your MF is plus or minus 1/2. Okay, so you have two states, two Zeeman states. Okay, now imagine that you are in the quadrupolar trap, so you increase the magnetic field along this axis. Since the magnetic field depends linearly on the position Z, you can also replace this axis by Z. Okay, so you have a linear dependency. And now what you do is you shine in a radio frequency. So you take a loop antenna and you plug in a 10 megahertz radio frequency also. What do you do? Well, if the frequency fits the frequency difference of your Zeeman state, you will couple them. Okay? But how you handle a two-level system, we already learned. So we have a Hamiltonian. And this is the Hamiltonian that we already learned in the first lecture. This one here. So in the off-diagonal element, you have the coupling terms, which is the Rabi frequencies here and here. Here I choose the energy, the zero energy point in the center between the two levels. So I have 1/2 of the energy for the upper level and one half of the energy in the lower level. But it doesn't matter. It's just shifting the zero energy. The physics remains the same. And now the detuning of the radio frequency depends on position, because there's only one position where the radio frequency is able to couple the two states. And this is at a very well-defined position Z. So imagine you have here a cloud of atoms, but only those atoms which are located at this distance from the center will be able to see the radio frequency and will be able to do transitions here. So actually this is used for evaporation. So imagine you have a very strong, very hot cloud, which is distributed over many energy levels here. Then those atoms which have higher energy, they have a probability to reach this point. So they're converting all their kinetic energy to potential energy. They can oscillate to this point, and then they can undergo a transition to this state and then leave the trap. So you get rid of the hot atoms. Okay. So only those atoms which are cold, which are cold enough to not to reach this point, they remain in the trap, and all the hot atoms are removed. So this is a radio frequency evaporation technique, which was the technique which was able to make Bose-Einstein condensation. This was the breakthrough, let's say. And then you reduce the frequency of your radio frequency. You just take your synthesizer and you reduce a little bit the frequency of your radio. And then that means that you move this knife, this radio frequency knife, a little bit closer to the center, and you get rid of those atoms which are a little bit hotter, but a little bit colder than before, but still the hottest atoms. You always remove only the hottest atoms if you do this slowly enough. Yeah? This is called forced evaporation. And at the time, you lose a lot of atoms, because normally you lose 99.9% of the atoms, but the 0.1% of the atoms that remain, they are so cold that they automatically undergo Bose-Einstein condensation, phase transition. Now, in this context here, there is another interesting feature. Since the two levels are coupled here, what happens is light shift. Okay, so if you couple two levels, they will split up. And the splitting will be just the Rabi frequency. No? This is the Adler-Towns splitting. This is what is illustrated here. So you should visualize it in this way. So you have these two levels. These are the bare states. And now you have here the radio frequency. Now I draw the dressed state. The dressed state is just the ground state plus one photon. The photon is this one. So I draw this state shifted by the photon. So now I have two dress states, which is this state and this state, and they cross. And if you couple two levels by a radiation that cross, what you have is an avoided crossing. That's just another word to say that there is a light shift. So the real adiabatic potential that you will have, they look like this. This crossing does not actually happen, but it's avoided because those two levels they push each other away. Now imagine that you have an atom here, okay, or let's say you have an atom here. Instead of going back all the way here, it will. What it does is it follows adiabatically this potential, and it can be trapped in this adiabatic potential. So this is a trapping potential here. If the atoms move slowly here, you can just trap it around the position that you defined by your radio frequency. So and then by changing the radio frequency, you can change the position of your trap here. Okay. So you can manipulate and artificially construct trapping potentials also by using this trick, by coupling different Zeeman states by radio frequency. So it's a really extremely rich and powerful toolbox, and this means many things that have not been exploited or are not currently exploited in every lab today. Okay, so this is I'm at the end of this part of the lecture, and yes, are there questions? No, then.